Now, of course, this is an enormous open problem. It's the subject of this conference, this program. And so for my talk, I'm going to narrow the focus to a specific tiny piece of this overarching question, which is the following. I want to ask, does string theory involve a sum over topologies or not? To be clear, I'm asking this question about the putative non-perturbative definition of string theory. I'm not asking this question about semi-classical gravitational path integral. And this is an old question. There are strong arguments that have been made by many people. I'll review some of them on the next slide, in both directions, both that we should or that we shouldn't sum over topologies in whatever the non-perturbative definition might be. Now, of course, to completely answer this question, we would need that non-perturbative definition in hand. Of course, we're not going to do that right now. But what I'd like to convince you today is that we actually already have enough information, sort of extrapolating a bit, to make a very good educated guess as to the answer to this question without a non-perturbative definition. So what I'm going to do concretely is I'm going to give the sketch a schematic argument that a sharp answer to this question follows as a logical consequence of two general principles we believe to be true of quantum gravity. The first of these is the idea of ER equals EPR. Of course, ER equals EPR can mean many different things. I'm going to use a particular interpretation of ER equals EPR that I'll hopefully convince you is reasonable and is actually just a small extrapolation from familiar stringy physics. And then the second step will use this swampland Cobordism conjecture of myself and Cameron Vafa. If you're not familiar, this is essentially just a reformulation of the idea that quantum gravity has no global symmetries. But it's a particularly useful reformulation for answering exactly this question. So before I present the answer I'd like to argue for, I'd like to just review these arguments that have been given, pros and cons of a sum over topologies. These are probably familiar, but I'd like to go through them because I would like to make it clear that the arguments in both directions are very good. They're convincing arguments. And so no simple yes or no answer could potentially be satisfying. Okay, so what are some pros? Well, as I see it, the first reason why we should sum over topologies is just on the basis of general principles of gravity and quantum mechanics. Quantum mechanics says that if we want to treat a system quantum mechanically, we should sum over all dynamically allowed processes in a path integral. And we know that string theory involves dynamical topology change. We see this all over the place. So if you put those together, it seems like there's no option. Sort of a sharper version of that is that if you tried to make any non-local restriction on the sum over topologies that could not be imposed by any local rule, then this would manifestly violate the equivalence principle or the idea of general covariance. So those are some aesthetic reasons to think we should sum over topologies. There's also lots of good practical reasons, which is that the sum over topologies frequently gives the right answer. An old example of this is the calculation of the black hole entropy from Euclidean Schwarzschild saddle. You can argue for the Bekenstein-Hawking formula from Lorentzian considerations and from consistency of thermodynamics, but the easiest way is to go to Euclidean signature, include a non-trivial topology, and just read off the answer. Now, more recently, we've learned that the sum over topologies knows much more detailed information about quantum gravity than we may have thought. It's been shown that replica wormholes can be used to derive the page curve or violation of global symmetries, which are much more detailed information than just the black hole entropy. Good, so these are some, I think, very convincing reasons to sum over topologies. These are good features we would like of a non-perturbative theory of quantum gravity. But I think the arguments against a sum over topologies are equally strong. So the first problem with the sum over topologies is that it leads to a loss of unitarity. This can be seen in the work of Coleman, Giddings, and Strominger on Euclidean wormholes and baby universes. What they showed is that if you include them in your path integral, you either have a breakdown of quantum coherence or the appearance of an ensemble as opposed to an individual unitary quantum system. But you can actually see the loss of unitarity more simply in the basic black hole information paradox. Just as you can calculate the black hole entropy from a non-trivial topology, you can also view the black hole information paradox as arising from including non-trivial topologies in your Euclidean path integral. Closely, yeah.
Can you explain that? That seems like a very strong.
Sorry, where's? Oh, yes.
What non-trivial topologies are you describing as giving a loss of information? I think
The Euclidean Schwarzschild solution. This is a distinct topology from the thermal vacuum. So closely related to the loss of unitarity is the fact that you cannot Wick rotate non-trivial topologies back to Lorentzian signature. It's a fact that if you have a Lorentzian metric on a complete manifold, the Cauchy slices will be diffeomorphic. And so there's sort of no first principle reasons from Lorentzian signature why you should include non-trivial topologies in your Euclidean path integral. Now, I think the sharpest issue with the sum over topologies is the factorization paradox. This has been discussed in very many contexts. In fact, a little bit of it is apparent even in Tufts' original paper on holography. This is the fact that wormholes spoil the factorization inherent in holography. Holography tells you that gravity is a local quantum system on the boundary, and wormholes connecting disconnected pieces of the boundary spoil factorization of correlation functions or Hilbert spaces. So this is a very severe issue and must be avoided in any theory which is both UV complete factorizing and includes the sum over topologies. So how can we get around this paradox? This is a very sharp tension. And I think you might even expect that this is actually a direct contradiction, that these are fundamentally incompatible. To illustrate that they're not fundamentally incompatible and that there is actually a way out, I want to review a beautiful example where we know how this question is resolved. So this is the tensionless string considered by Eberhardt, Gabriel, and Gopakumar. It's the NS-NS flux background, ADS3 cross S3 cross T4, in a single unit of NS5 flux. And what's so beautiful about this theory is that in this theory, the worldsheet path integral, or the worldsheet CFT path integral, localizes on configurations which are supported on the boundary, which is what I've tried to draw here. Here's a string sitting at the boundary of ADS3. Now, what Lawrence Eberhardt pointed out in a very nice paper is that this property means that the tensionless string partition function in this theory is completely independent of the choice of bulk topology. No matter what you put, you get the same answer. And what this means is that there's no need to sum over topologies. You just pick one. Of course, you could sum over topologies. If you did, you would just get an overall multiplicative factor. Maybe you should divide it out. But even just fixing one topology, the other topologies, Lawrence argues, should be already there, included as stringy condensates on top of the fixed topology you chose to define your theory. So the interpretation, the words I'd like to put on this, is that I'd like to interpret in this theory the choice of bulk topology as a gauge choice. I'd like to say that in this theory, the bulk topology is pure gauge. We could sum over it, but if we don't want to overcount, we should gauge fix. We should pick a particular topology. It doesn't matter which one we pick. And in this way, this theory is not defined necessarily in terms of a fixed topology, but we can write it in terms of a fixed topology by means of gauge fixing. So I'd like to discuss to what extent this picture generalizes. Of course, the localization is particular to the tensionless string. This is a very special theory. This is far from true in general, of course. But what I'm going to argue is that the same general answer should be true in any UV complete theory of quantum gravity. In particular, I'd like to argue that in string theory, in general, we should think that the sum over topologies is pure gauge. It's just summing over gauge redundant descriptions of the same physics. And I find this a satisfying answer to the original question. It synthesizes both alternatives as gauge equivalent. So if we want these sort of aesthetic properties of summing over topologies, we can do that. But if we want to avoid any particular paradox coming from summing topologies, well, we can just gauge fix to a topology where it doesn't arise, and then if something's true in one gauge, it's true in every gauge. So this is a bold statement. I'm certainly not going to prove it. At best, I'm going to sketch a reason why you might believe this. And the logical structure of my argument is as follows. First, I'm going to interpret ER equals EPR as a particular sort of gauge redundancy in quantum gravity that relates topologically distinct manifolds. More precisely, I'm going to argue that it relates spacetime manifolds which are cobordant, which I'll define. And that puts us in a perfect position to just impose the Cobordism conjecture, which I'll also review, to connect all different topologies in a single gauge orbit under ER equals EPR. And as a result, we would be able, if this is true, we would be able to gauge fix the sum over topologies to any fixed topology we like.
Question?
Yes?
In your motivated example, you don't have dimensionless large scale where you usually have this, right? Then we know that non-perturbative partition function you must summate.
Do you mean if you want to interpret it in terms of a semi-classical saddle point approximation?
Yes.
Yeah. I'm talking about the non-perturbative, the full. I agree that if you want to do semi-classics, you need to consider distinct topologies as possible saddles. But that's because you don't have control of the complete UV complete stringy theory, right? If you could actually directly compute in the stringy theory, what I'm arguing is that you should be able to see the same physics without summing over topologies. Say by summing over stringy degrees of freedom on a fixed topology. Non-perturbative. I mean, it's similar to what you discussed in your talk, right? Which is that you viewed one topology as dual to a distinct topology where you had microscopic degrees of freedom. It might be that for a particular question, one description might be better, right? Duality, for a particular question, different dual frames are not necessarily equally good for answering the question. But in principle, they should both be able to contain the same physics. Yeah.
In your point of view, can you describe some topologies arising in one particular picture as a singular gauge choice so that actually those topologies are because of the bad gauge choices?
That's an interesting question. I don't have a direct answer, but that's an interesting question. Yeah.
Are you saying that in the context of the given Hawking paper from 77, I could take the S1 times R3 topology and still get the black-hole entropy result?
The perspective I'd like to advocate for is that you could pick that topology and you would get the black hole entropy by including non-perturbative stringy degrees of freedom fluctuating on that topology. I'm not saying you can see it semi-classically. Yeah. Great. So the main sort of thing I'll have to do is this first step. I'll have to convince you that you can think of ER equals EPR this way. So let's do that. So first of all, I think it's not always said that ER equals EPR is a gauge redundancy. Before I explain that, let me just make a basic observation. This is pointed out in these two nice papers. The fact that there are gauge redundancies in quantum gravity that relate distinct topologies is kind of clear from some basic facts about quantum gravity. If we believe in dynamical topology change and we believe in a Hamiltonian constraint, then because the Hamiltonian constraint tells you that any bulk dynamics is pure gauge, then any bulk dynamical topology change is pure gauge. So it's kind of intuitive from that perspective that we should have gauge redundancies that relate distinct topologies. Now that statement as just by itself is not necessarily the most useful. What's going to be useful is that we have a schematic proposal for the form that these redundancies take. So this is ER equals EPR. This is the idea that wormholes should be gauge equivalent to particular entangled superpositions of disconnected microstates. I've drawn here the most, I think, explicit example of this, which is Maldaceno's identification of the ADS Schwarzschild wormhole state as a particular superposition of disconnected states. Now, why do I call this a gauge redundancy? Well, a gauge redundancy is a physical equivalence between quantum states that look naively distinct. And that's what we have here. On the left, we have a wave function supported only on a single smooth wormhole geometry. And on the right, we have a wave function supported on disconnected configurations. Of course, I've drawn a star to represent whatever stringy stuff is making up the black hole. The difference between this and an ordinary, the familiar gauge redundancy, is that familiar gauge redundancies act to take you from one classical configuration to another classical configuration. Here we're taking a classical configuration to a quantum superposition of configurations. Yeah?
Are you going to distinguish between these kind of spatial wormholes and space-time wormholes?
I'm going to argue that you can think of them the same, but I'll comment on that distinction. Yeah. Yeah.
So when you have gauge symmetry,
Yes.
you have two things. One is that you have constraint,
Yes.
and the other is identification of two equilibrium. So you
Yes.
have the latter.
The next slide is the latter. Yeah. Okay, so as Hiroshi says, gauge redundancy is not just a constraint on the Hilbert space, but it's a redundancy between configurations in the path integral. You can see this via Einstein's whole argument. If you have a redundancy in space that isn't a redundancy in space-time, then your theory becomes non-predictive. So let's try to see how we can apply ER equals EPR to a space-time, to a history. So I'm going to take a smooth geometry. I'm going to call it Einstein-Rosen gauge. And this is the smooth geometry I've tried to draw, which represents a virtual Euclidean black hole loop. I'm not being careful about the metric or anything, but what we have is we have a black hole horizon running in a loop, and that horizon, the Euclidean time circle, closes off in a cigar. And what I want to do is I want to take this history, and I want to slice by slice apply ER equals EPR, and I obtain the right-hand side picture. So I'm going to call this EPR gauge. This is a coherent sum over microstates, distinct microstates, running in a loop on top of a distinct topology, on top of a topologically trivial spacetime. And so this is the sense in which ER equals EPR replaces a non-trivial spacetime topology, or one spacetime topology with a different one. Now, to go on, I need to sort of piece out exactly how the topology changes. So in Einstein-Rosen gauge, ER gauge, we have Euclidean Schwarzschild, at least locally near the object. We have a sort of cigar, which is topologically a 2-disk, and we have a horizon, which is a d-2 sphere. On the other hand, in what I've called EPR gauge, we still have our Euclidean time circle, but instead now the horizon pinches off, as we saw in the previous talk. The horizon pinches off and closes on something that you might be able to view as a microstate. So this is a basic operation in differential topology. This is known as a surgery. Surgery is where we have some region, which is a product of a disk and a sphere. We cut it out. We glue in having the other cycle pinch off. So this is a surgery of a particular dimension because we've considered a black hole, a black particle. More generally, we might want to consider black p-branes of various dimensions. And so we can understand general surgeries on the space-time manifold as geometric transition. This is an extremely familiar thing in string theory, where we have, again, a product of a disk and a sphere, and we switch which cycle closes off while introducing some state of wrapped branes on the dual cycle. This, of course, is the basic geometry of holography as realized in string theory, going back to Maldasena's original paper and plenty of other places. So the assumption I'm going to make my argument, I'm going to call it space-time ER equals EPR, is the assumption that space-time manifolds, which are related by a simple surgery, are actually gauge equivalent configurations in the path integral, up to including an appropriate condensate of wrapped microstates. And I'm going to close my eyes and not be careful about what those are, but the assertion is that there exists such an appropriate condensate to realize the alternative geometry. This is sometimes how we think about geometric transition in string theory. Sometimes we think about geometric transition as moving to distinct points in moduli space. And the difference from there is that we've actually included a condensate of branes to represent the dual cycle. So to sort of illustrate what I mean by this in more examples, maybe convince you this is a reasonable thing, let me give you two maybe more explicit examples of this type of space-time surgery. So the first is that we can cut Euclidean wormholes if we make the assumption, which many, many people have argued for, I've probably missed some, that the Hilbert space of closed universes in quantum gravity should be a one-dimensional Hilbert space. Now, I'm not going to argue for this here, but if we take it as a given, then we have the following. We have an equation. We can decompose the identity operator acting in the baby universe Hilbert space as the product of the Hartle-Hawking ket with the Hartle-Hawking bra. And we can insert this in the path integral. So suppose we have in our Euclidean path integral, non-perturbative path integral, we have some Euclidean wormhole, space-time wormhole. I will insert this equation along a spatial slice, and we'll learn that this wormhole is actually equal to the same configuration away, but in the middle we replace the smooth geometry with the product of the Hartle-Hawking ket with the Hartle-Hawking bra. So this is sort of ER equals EPR for space-time wormholes. So this is maybe a more speculative example to give you a very concrete example where you can do calculations. I'll point to the topological vertex. So in the topological A-model string theory, when geometric transition is possible in the moduli space, you can perform Gopakumar-Vafa duality locally in your Calabi-Yau threefold, maybe non-compact Calabi-Yau threefold, by performing surgeries. You take your manifold, it's a smooth manifold, you want to compute the topological A-model partition function, and you do surgery, you introduce Lagrangian branes, and you compute it as equal to the partition function on a dual manifold. And so I'm viewing this as an example of spacetime ER equals EPR. Let's see how I'm doing with time. So I've argued that if we assume ER equals EPR, we can replace any spacetime manifold M0 by a sum over stringy degrees of freedom on any other spacetime manifold M1, which is related to M0 by a sequence of surgeries. Now, when is a manifold related to another by a sequence of surgeries? This is a textbook fact in differential topology. Two manifolds are related by a sequence of surgeries if and only if they are cobordant. So cobordant means that M0, or its orientation reversal, and M1 are mutually the boundary of a manifold one dimension higher. Just to sort of explain the equivalence, if we choose a Morse function, every time we pass a Morse critical point, the slice will change by a simple surgery. So this suggests a gauge fixing algorithm. The first thing we do is we take all of the manifolds in our gravitational path integral, we group them into Cobordism classes, so equivalence classes by this relation, and in each Cobordism class we pick a particular representative topology. Now every other topology that isn't one of those representatives, we absorb as stringy excitations, maybe additional stringy excitations, on top of the chosen representative. So this almost gets us all the way, but we still have distinct gauge orbits. So to get rid of this last issue, the fact that we still have to sum over the distinct Cobordism classes, well, Cameron and I thought about this in a paper in 2019. We put forward swampland conjecture, which has become known as the Cobordism conjecture, which is the idea that in string theory, we should expect that all space-time manifolds of the same dimension should be cobordant, taking into account appropriate quantum gravity effects. So the argument we gave there was based on no global symmetries. We said that the Cobordism class is a conserved global charge, and quantum gravity should not have conserved global charges, so we conclude that they should all lie in a single Cobordism class. We see here a possible alternative motivation for this Cobordism conjecture, which is to say that, first of all, that you believe me, and that we should use ER equals EPR as our way out from the paradoxes of sum over topologies. We can only do that if the Cobordism classes are trivial. In other words, Cobordism quantifies the topological obstruction to using ER equals EPR as the resolution to things like the factorization paradox. I discussed this a little bit in my thesis. So if we just apply the Cobordism conjecture kind of blindly, the sort of statement as I've stated it here, this would conclude the proof. We would learn that all topologies would be in a single gauge orbit. Now that's certainly a little too fast for many reasons, but for one particular reason, which is that string theory certainly involves moving beyond smooth spacetime manifolds. We need singular spacetimes, we need non-geometric spacetimes. So what do I even mean by Cobordism? Well, one thing I'd like to say is that you can sort of turn the argument around. You could define the Cobordism classes of quantum gravity as the irreducible sectors in the sum over topology once we take these gauge redundancies into account. The conjecture would be that in UV complete quantum gravity, there should only be a single class. To sort of illustrate what I mean by this, let me give a more specific example. Before we completely abandon geometry, let's talk just about manifolds with prescribed sorts of singularities. So these are objects that can be referred to as Cobordism defects. These are objects which trivialize an otherwise non-trivial Cobordism class. These are the objects which are required by the principle that string theory should have all objects of all possible charges. This is a possible charge an object can have. To give you an example, a paper from before ours by Tachikawa and Yonakura explained in what sense RP5 describes a non-trivial Cobordism class in type 2b. In fact, they described all real projective spaces in this way. Now, type 2b, is in the landscape, and so should not have a global symmetry. And type 2b has exactly the object required to trivialize this cobordism class, which is the O3 plane, R6 mod Z2 singularity. The O3 plane is topologically a cone on RP5. And these have well understood what role these objects play. These objects provide the necessary microstates for wormholes whose cross-section topology of their horizon realizes a non-trivial class in cobordism. So in this example, if we wanted to talk about the microstates of black brains whose near horizon geometry even is ADS5 cross RP5, well understood what those are. Those are D3 brains probing an O3 plane, as described in these papers. And so what is ER equals EPR? Again, if you believe what I've been saying, for these types of wormholes, well, it's a sort of generalized surgery. So the ADS5 here is topologically D5, and the horizon is RP5. Now, it's not a sphere, it's a different manifold. And we switch which one is filled in. We have the S4, which is the world volume of the object. And we have that the RP5 closes off and terminates on this Cobordism defect, this space-time singularity. And so if we really want, if the picture I've been describing should work, we need ER equals EPR not just for black brains whose horizon topology is a sphere, we need it for arbitrary such objects, and in fact we also need it off-shell, which is something I've kind of been sweeping under the rug. Before I sort of wrap up, I think I'm doing, how are we doing? Yeah. Before I wrap up, I'd like to mention even if it hasn't been speculative enough, an even further speculation, which is that in every quantum gravity theory, there's a universal Cobordism defect, because there's a universal Cobordism class, which is the Cobordism class of a single point. So a single point is not the boundary of any one manifold. To be a boundary of a one manifold, you need the one manifold to come off and end. And so you need an end of the world brane. And this is essentially the same reason as people have also discussed end of the world branes, or half wormholes in the context of the factorization paradox. So what does it mean to have a wormhole whose horizon topology is a single point? Well, that's just the space-time vacuum itself. The space-time vacuum, the internal geometry is a single point. That's sort of a tautological statement. And if we try to play the same game and do a generalized surgery, then we take an arbitrary region, we hit it with ER equals EPR for end of the world branes, and we obtain the entire interior has been cut out, and we have some degrees of freedom propagating on the boundary. So if what I've discussed extrapolates even to this case, then we obtain a very naive version of the holographic principle. In this case, it could be understood as part of the gauge redundancy structure of quantum gravity, that you can take a region, replace it by gauge transformation with an alternative description, but one which you can do locally in the bulk, not just for the entire space-time at once. I should mention that this example of a surgery is actually realized explicitly in the stringy ER equals EPR of Jafferson Schneider, also in Horowitz-Polchinski. This is an understood surgery or generalized surgery in particular cases. So let me sort of wrap up. So I've argued that we should view ER equals EPR as a gauge redundancy of string theory or of quantum gravity, which you can understand as a local version of holography. Instead of doing holography for the entire space-time, you do this geometric transition just piece by piece. Given that, I identified Cobordism as the topological obstruction to entirely gauge fixing the sum over topologies away. Applying the Cobordism conjecture, we learn that in string theory, the sum over topology should be pure gauge. You should be able to do an appropriate gauge fixing to get rid of the entire sum over topologies at the expense of introducing potentially lots of stringy degrees of freedom. So I should say that this argument is extremely speculative. This is a sketch of a heuristic sketch of a logical structure. This is not a proof. And there's lots of aspects of this I'd like to study more. And in fact, I'd like to say, if anyone has any thoughts on making any aspect of this more precise, please tell me. I'd love to discuss. I just wanted to advertise one aspect of this that requires further study, which is the question of how do you organize the combinatorics and the recursive structure of this gauge fixing. I told you what to do for a single surgery, but there's an entire sort of recursive structure of how you organize that combinatorics. And I just wanted to point you to an upcoming paper of ours with Elliot Justeau and Matilda Marcoli, where we described sort of a gravitational analog of the BPHC algorithm for handling this question. So thank you for listening, and I look forward to your questions.
So I just have a suggestion on how to make this a bit more precise.
Please.
It seems to me that the sum over, what topology to sum over is a little similar to what field configuration to integrate over in the Wilsonian framework, where you get to, set your floating cutoff. If you vary that, you have the answer is different.
That's right.
And so I would also expect that a different effective description where what topology to sum over is different. And it seems like you're suggesting that there's some, it's like taking the Wilsonian cutoff all the way to infinity. I
completely agree with that perspective. I think that's a really good way to think about it. And in particular, I'd say that this is related to the Wilsonian perspective of the bulk field, the bulk theory, right? In the IR, we have semi-classical gravity where we should sum over topologies. They're physically distinct. And then once we include the UV degrees of freedom, which make up black hole microstates, then we have a reduced description.
I had a question regarding how singular you can go. So you mentioned, the Cobordism defects is sort of grouping for you singular configurations and giving you some organizing principle. Is there a clear statement of how singular a background one should include in this count?
That's an excellent question. A very easy way to satisfy this Cobordism conjecture is to say that you make absolutely no restriction and have a cone on every possible manifold, and then clearly there's no invariance. In practice, in string theory, I think that maybe, as Xian was saying, you might want to think about different scales. And maybe in the deep UV, you should think that anything goes. But in intermediate scales, you expect only to have sort of prescribed singularities, as we see in string theory, right? In string theory, we are, at least in the supersymmetric context, we don't allow any arbitrary singularity. There are prescribed singularities we allow. So that's how I would think about that.
Great, thanks. Just one quick follow-up. Is there any sort of global constraints that are easy to state about how many surgeries one can do in one orbit of the theory?
That's a great question. I don't think there's any bound. I think there are cases where you can do as many, arbitrarily many. I'm not positive about that, but I believe that's true.
Thanks.
You sort of answered the question, but sorry. Did you want to go? Okay. Could you comment more about the non-geometric states?
Yeah. So the definition we actually gave in our paper from 2019 is we define the Cobordism classes of quantum gravity as configurations up to finite action processes. And so that is manifestly well defined even for non-geometric backgrounds. You can talk about the quantum gravity defined by string theory compactified on a non-geometric space and another string theory compactified on a geometric or non-geometric space, and you can ask, is there a finite tension domain wall between those theories? I don't know any way to motivate the need for non-geometry directly from this conjecture, but I think the fact that it exists in string theory kind of suggests that it has to be part of the story.
Thank you.
So that was actually my question. But maybe let me follow up one little bit on it, which is for the case of like going to some non-geometric theory, how do you envision that like the surgery procedure would work for that?
Excellent question. Excellent question. The truthful answer is I don't know. It's clear from the answer to the previous question that in some sense, some degree of topology still exists when you don't have geometry. You can still talk about, there's still a natural notion of Cobordism of such things. So I would hope that this equivalence would maybe define a sense in which you can do surgery, but this is speculation. I should also say, of course, it's also clear in other contexts that the topology of a non-geometric space has some meaning, right? So, the mirror of a rigid Calabi-Yau has a Hodge structure, right? So there's still some topology. It's just not realized geometrically.
Yeah, I was going to follow up on a question earlier from Samir about the ADS3 example. So you gave examples of how factorization how this could work with defects, but the examples were all things where defects were stringy excitations or debrins. To actually get the full partition function in these examples, you also need objects which would be much heavier. So do you have comments on how that might work?
When I said stringy types of non-perturbative effects, I don't mean strings. I mean things like D-branes, and yeah, that was just a terminology. In this example, because you have a tensionless string theory, you actually just need strings, but that's particular to the fact that it's an NS-NS flux background. Right.
Can I go? No, Veronica.
Okay. Would you imagine a possibility of going the other way, of mocking up all the non-perturbative, stringy, and whatnot degrees of freedom with just topology?
Yeah, I mean, again, I think you can sort of go to this sort of Wilsonian perspective that maybe you think in the UV, the theory is defined. I mean, in ADS CFT, you could think the UV is defined by the CFT degrees of freedom. But maybe you think that in the UV, the theory is defined by a single topology and stringy excitations on top of it, any single topology. And then as you want to integrate out those degrees of freedom, those degrees of freedom should lead to emergence of additional spacetimes. And so I think in the IR, you can view that as coming from integrating out the stringy degrees of freedom and replacing them with smooth geometry, which makes sense in the IR even if the microstates do not.
Actually, sorry, can I ask? Yeah. My question was also related. So there are examples known where you can push the sum over saddles to great precision, and you know that that's correct. So is this just some tautological thing saying that that is the answer, or is there some a priori prescription which you're giving which will reduce to that?
So I'm certainly not giving an a priori prescription. I'm not answering this question, this deeper question. What I'm trying to sort of explain is a necessary condition for there to be no invariant information in the sum over topologies. That doesn't mean you can't use it to do a saddle point calculation. It's just I'm saying that if you believe these two broad and not sharply defined things, then you learn that you can do this sort of gauge fixing.
Maybe to just follow up on that question, I'm here. In the examples that Samir talked about for indices, we explicitly know that at the level of the gravitational path integral, we have to sum over saddles with different topology in order to get the right answer. Is your claim that all those saddles that have different topologies belong to the same Cobordism class? And if so, have you explicitly checked that for all the index examples that are known?
That's an excellent question. No, I haven't checked it.
Sorry, this was also my question. Before checking it, what are you checking?
Sorry?
I mean, no, it's not a joke.
Absolutely fair question.
I'm just asking, what is it that you're trying to calculate? That's what my question is.
I'm trying to speculate as to this non-perturbative definition of string theory. I'm not trying to verify this by some calculation, but of course, that's part of the making this sharper. Yeah. I would point to the topological vertex as an illustration of this type of thing in practice.
Yeah. So I guess you've been a little abstract about what this gauge symmetry is going to be and what the degrees of freedom are, but I'm wondering in this simple n=1 ns flux background, whether they have some ideas of making this precise, like you may, maybe two different topologies differ by a Q exact term in string field.
I mean, it's kind of. Oh, in that sense, I'm not sure. It might be contained in this paper. I'm not positive. But the gauge redundancy in this case is like completely tautological. It's just you can completely replace the bulk with any other bulk you want at completely no cost to the physics.
But you'd want some degrees of freedom, and at least the way I think about gauge symmetry, you want some extended degrees of freedom that, with some symmetry acting on it, and there's some gauge slice that then looks like some sigma model on one target space, and a gauge slice that looks like a sigma on another target space, and maybe another gauge slice that is just the boundary CFT.
So in this example, it's completely explicit. The additional non-gauge invariant degrees of freedom are the choice of the bulk topology. There is a one-to-one gauge redundancy between any two of those, and so any given one is a slice of the gauge orbit. It's totally tautological, but I think it's what's happening in this model.
So suppose we took the worldsheet theory and thought of it to the 2D theory of quantum gravity. Would the statement of this kind apply?
Yeah, I mean, this is the sort of thing that's realized in this stringy ER equals EPR, right? So worldsheet duality between distinct topologies related by assertion.
So what is string? So you'd say the string perturbation theory is just an accident of us not knowing how to implement this?
No, I mean, I think that this question isn't visible in string perturbation theory, right? And, well, yeah, it is about Spacetime.
I'm just asking the worldsheet theory.
Oh, the worldsheet quantum gravity on the worldsheet. Ah, okay, good. So the worldsheet quantum gravity, my perspective is that the worldsheet quantum gravity should not be viewed as analogous to target space quantum gravity for the following reason. It violates so many principles we believe to be true of quantum gravity. It has global symmetries. It has non-trivial Cobordism. It's not, what I've described is not true for the worldsheet topology. So worldsheet theory of quantum gravity. So for example, JT gravity as a worldsheet of a topological string is an ensemble. It's not a particular unitary theory of quantum gravity.
So you'd want to say that low-dimensional gravity theories are somehow special and they allow multiple interpretations, but higher-dimensional gravity theories are somehow more constrained? We
discussed this in our paper from, I guess, 2020 on baby universes. The perspective that I have is that in low dimensions, quantum gravity, you don't need UV complete quantum gravity in the sense that we usually mean, because the theory can be renormalizable. You can just do the gravitational path integral. But the thing that you produce should not be viewed as conceptually analogous to what we usually mean by quantum gravity, that has black holes, that has holography, that has microstates, these sorts of things.
Thanks.
Sorry.
I apologize for having, is this on? Yeah, for having walked in late, but I think I can still ask a question that still seems to be relevant. I'm a little confused about, like everyone else, what it is actually you're suggesting. And I guess I have two questions. One is a basic one. I understand you'd like to get rid of sums over wormholes. Is that the same as removing all the sum over topology, or is that an extension?
So the argument I gave was precisely that if you can remove wormholes and you have no global symmetries, then you can remove the entire sum over topology. That was the logical structure.
Great. Yeah. And then I'm trying to decide what, okay. As you say, in a low-dimensional example, where there is an ensemble, there's also a way to get rid of the ensemble by using the, baby universe alpha states or something of that kind. And I'm trying to understand, are you saying anything different than, again, the idea that there's a single such, let's call it an alpha state in higher dimensions, or is this a different kind of?
No, this is equivalent to that assertion. It's equivalent to, you need a little bit more. You need a single alpha state, and you also need all the higher codimension analogs of that, because you need it to be true not just for Euclidean wormholes, but spatial wormholes and black brains. But it's just that assertion. And I should also say that in this paper, we're going to discuss a low-dimensional example, actually this same one as has been discussed before. We're going to explain how you can do this sort of gauge fixing at the level of the gravitational path integral.
Okay, so it's worth mentioning that although there's always this discussion of how can you get rid of topologies and yet have the semi-classical approximation, I mean, in those low-dimensional examples, like, say, JT, we see exactly how it's done, because you can do it explicitly both, or actually, if you really want to sum the series on the bulk side, you can go to an even simpler, like, purely topological model, and you can just see exactly how it's done, and you can do both.
Totally agree.
Okay, great.
100%.
Is there a question from Edward on Zoom? You can go ahead and unmute yourself and ask.
Yeah. I wonder if we can interpret what you're saying as follows. So, in string theory, the topology isn't well defined. Therefore, in a phenomenological theory where it is well defined, you'd say that you're summing over topologies.
Yeah, I agree with that interpretation. Yes, I would say that again, you can think of it as the Wilsonian sense that in the infrared theory, the effective field theory topology is well defined, and saying that there should be no aspect of topology that's well defined in the UV complete theory.
Okay, let's thank Jake again.